So what we are going to do now is start with redesign 3, which already has the best practice loading and spanwise RV theta from the manual redesign, and then see if we can further improve we can further optimize this using automatic optimization in Turbo Design 1. So here is the workflow used by the optimization, where the blade loading parameters are used to generate the blade shape in Turbo Design 1, and then the resulting performance parameters are fed into the optimizer, which basically applies MOGA to take the solution to the optimum design. And of course, we need to start by specifying the range of variation for the input parameters, which are the streamwise loading as well as the spanwise RV theta distribution parameters. And whereas by default the ranges are set to plus minus 10% of the baseline values for each parameter, as you can see here, but there's a machine learning based feature in Turbo Design 1 that can provide initial range estimates for these streamwise loading parameters. And this is because we want to explore a large design space but also try and avoid infeasible solutions. But these spanwise RV theta ranges are set manually, where we extend the lower and upper bounds in order to provide sufficient play to the optimizer. And then these are the constraints that were used. So we constrain the throat to plus minus 10% to control the peak efficiency point, and then the overall diffusion ratio is limited to avoid flow separation. And here we have some Python scripted user-defined parameters as well. So UD work is actually indicative of the power consumption by the fan, and so we in fact constrained this very tightly. And then in order to avoid blade overlapping, for manufacturing reason, we have this UD overlapping, which is 1 for redesign 3 but needs to be 0 for the optimum design. And then these 3 parameters are actually used to avoid negative blade loading at the hub, midspan and the shroud respectively. And finally, for the optimization objectives, we want to minimize the total profile loss and the tip leakage loss, because as we saw earlier, they are the dominant loss mechanisms in axial fans. So once the optimization run is complete, which is very fast and only takes about an hour or so on a single core machine, we can see all the designs on the scatter plot between these two objectives. So the leakage loss on the x-axis and the profile loss on the y-axis, like that. And then the target case, which is redesign 3, actually sits here. So next we can choose to see only the feasible designs which respect all of our specified constraints. And then this here is the Pareto front of the optimum designs, from which we can pick and analyze any design of choice. And in this case we select the minimum profile loss point as our optimum design for further analysis and for comparison with redesign 3. And in fact this is what changed as a result of the optimization. So for the spanwise work distribution, you can see that compared to redesign 3, the optimizer has tried to reduce the work at the hub and the shroud in order to suppress the hub diffusion and the tip leakage respectively. And as expected, it has tried to increase the work near the midspan in order to maintain the overall work. And then the blade loading also shows a considerable change from redesign 3, and then as a result the optimized blade shape is clearly very different from redesign 3, as you can see here. And then here are the results for the optimized fan, and it's interesting to see the effect on the Turbo Design 1 parameters, where there is a significant reduction in the overall diffusion ratio and the profile loss as a result of the optimization, without any compromise in the tip leakage loss. And also looking at the front view of the different designs, you can see that whereas we had significant blade overlap in baseline and in redesign 3, it is completely avoided in the optimized impeller as a result of our specified constraint. And when we actually run CFD on the resulting geometry, what we find is a notable further improvement in the efficiency and also a corresponding substantial increase in the pressure rise levels. And in fact, we are now very close to the mainline estimate of 92%. And in fact, the total to static efficiency is even higher than the mainline estimate, which was about 30%. And finally, we analyzed the optimized design at three operating points, that is 90, 100 and 110% of the design flow rate. And then if you see the total to total efficiency comparison with the redesign 3, clearly the performance is improved over the entire operating range considered. And what's also interesting is that the optimized design is now peaking at the design flow rate, whereas redesign 3 was peaking at around 90% flow rate, which means that the optimized design actually has the correct throat area. And also a consistent increase in the total pressure rise over the entire operating range, as can be seen here.